Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
Gabriel Maicas is currently a PhD candidate in medical image analysis at the University of Adelaide. His research focuses on the development of machine learning techniques to automate and improve the performance of clinical diagnostic systems. Gabriel's general research interests lie in medical image analysis, computer vision, artificial intelligence, and machine learning. Previously, he graduated from Universidad Autónoma de Madrid with a double degree in mathematics and computer science, and received a master's degree in computer vision at Universidad Rey Juan Carlos. Well, Gabriel, welcome to the show.
Hi, Kyle. Thanks for having me.
Oh, the pleasure's all mine. I really enjoyed your paper. To get started, can you tell me a little bit about what the work you were doing was?
Our work is focused on the development of machine learning systems that are used by radiologists to improve their accuracy, speed of their diagnosis. So basically, we were trying to identify which patients are suffering from a malignant cancer.
We've seen a lot of interesting work of the machine learning community in medical imaging in the last few years. I've found that it really comes down to a lot of the data sets you have to work with. Can you tell me a little bit about the corpus you based your research on?
Well, recently we've seen that bigger data sets have been achieving great performance. But it seems that these improvements are saturating. So even though data sets are important, I think it's also very important to design new methods that can extract better information from this. So in our case, our data set is actually really small. We used 45 images from 45 patients to train, which is very small compared to larger data sets used in computer vision.
Yeah, so how does that break down? If you have 45 people, is that in each of the labeled classes, or what's the composition of the data set?
So we use 45 patients for training, right? But we first extract the breast region from the image. That means that we can train our system with 90 breasts. Out of these 90 breasts, 38 of them contain malignant cancers, and the rest either contain benign findings or they are healthy. Although I must say that all patients have been diagnosed with a malignant cancer, not all breasts are suffering from malignant cancer. So therefore, we can find breasts with either benign or malignant findings or that are healthy.
Gotcha. So it's 3 class labels then, is that right?
Yes. We have 3 class labels, but the problem we are solving is really a 2-class classification problem, because in the breast screening problem, we try to find malignant findings as opposed to healthy or benign cases.
So one of the things that really caught my attention as I started reading your paper was when you say that, the machine learning process of collecting a bunch of data, getting it labeled, train and test with k-fold validation, that sort of thing, that doesn't at all resemble how a radiologist is trained. I have to confess, don't have much of a medical background. Can you tell me a little bit about how a radiologist is trained?
Well, in radiologists, but in general, all of us, we don't learn a very difficult task at the beginning. So, for example, imagine the case of a kid that starts to go to school in year 1. You don't ask this person to solve an equation the first day. You first start by teaching the basic operations such as addition, subtraction, multiplication. You may then proceed to teach about variables, what is a variable, and then you may want to teach how to solve an equation. The training process of radiologists simulates is also based in this kind of process. You start with easier tasks first, and then you move on to more difficult tasks. And even more, related to what we've been talking about, small data sets, radiologists are not trained with lots of images. In fact, for each of these tasks that you train radiologists on, the number of images that are shown to them has orders of magnitude less data than machine learning systems use.
It almost seems like these are data sets so small, they teeter on the usefulness. Half those examples, maybe you couldn't get anything done. It would be nice if you had more, because obviously more does seem to be better, but I imagine that must be prohibitive, either due to cost or rarity of disease or something like that. why are the data sets so small?
Well, obtaining large data sets that are properly labeled, it's really expensive, both in cost of money and time. So that makes it really, really difficult to obtain. Because current machine learning systems, you don't only need the data, but you need what we call strong annotation. So normally you will need the localization and delineation of the possible lesions, which is really expensive to obtain. Let me say also that machine learning research in for medical image analysis is also tending to incorporate all these data sets that we have at hospital and that contains what we call weakly labels. That means that each image may not have the localization of the lesion, but you have a global label for that particular image. And precisely our approach, what it does is instead of traditional systems that will need that localization, you will try to analyze the whole image using this weak label, which is cheaper to obtain, to predict the probability of malignancy.
So one of the novel ideas in the paper is the concept of metatraining. Can you tell me what metatraining is?
Well, let me start by saying how we normally train these systems. So current systems are normally based or are normally trained with image label pairs, right? Then in the inference phase, or when you give a nuanced image, you try to predict the probability of malignancy. But there is this new idea in the field to learn how to solve new tasks or classification problems in our case. And instead of using image label pairs to train your system, we ask our system to solve different tasks that are ultimately composed of few image label pairs, such that when you give a new task or classification problem, such as the breast screening problem, the system can adapt to it and solve it with a better accuracy and a better generalization in general.
So when you say you ask it to solve a different task, is that something totally related, like, looking at, cartilage in the knee, and then you transfer to the breast cancer screening, or is it something else? What are the commonalities of these different tasks?
Well, so all this new field is in an early stage. So we humans, for example, we can extrapolate, and given our knowledge in some tasks, we can infer or we can adapt to new tasks quite quickly, right? And with good precision. However, these systems are at a very early stage. For example, it's very difficult to imagine a robot that is learning how to grab a chair, the task of grabbing a chair, and then it's going to be able to identify if an image has malignant cancer. So there must be some kind of relationship, right?
Yeah.
So all this idea has been really popular in the few-shot learning. So basically, you try to learn from for example, from 5 images. You train your system with 5 images of each class, and then you want to classify new images of those class. So the problem is in itself a classification problem, right? But you are trying to solve many classification problems. It's not a classification problem as opposed to a grabbing a chair problem.
Well, it occurs to me that when you have so few examples, those medical images, even if they're at low resolution, there's a lot of pixels there. So there's a large dimensionality to this problem, probably more features than you have observations, in which case there should be an infinite number of linear separations from a machine learning point of view. How do you constrain the problem to work on such high-dimensional data?
Well, our data in this work was 3-dimensional, and it was 100 by 100 by 50, which is a lot of information. What we found is that instead of using these high-capacity models with millions or even millions of parameters, we could design a very small model, and we are talking about 26,000 parameters, and by training it properly, we can achieve good accuracy. In fact, we found that we don't need such a big model. If we look at the methods we compare with, you can see that what is known to be a high-capacity model to solve very difficult classification tasks, We use it, but in a very reduced way with fewer number of parameters. And that improves the generalization, which means that improves how well the system will predict the probability of malignancy given a new unseen image.
Could you tell me a little bit about those other methodologies that you compared to your work?
Yeah, so we compare with DenseNet, which is the state-of-the-art model for a classification problem in ImageNet. We also compare with what is called multiple instance learning, which is the state-of-the-art for the same problem, but applied to mammograms. And this multiple instance learning is based in considering the probability of malignancy for a particular image can be thought as the highest probability of malignancy of a particular patch in the image, assuming that you have divided the image into patches. And finally, we also compare to what is called multitask learning. So basically, because we are learning from different tasks or classification problems, you can also train a model that is capable of solving at the same time all those problems. And what we've seen in our experiments is that our meta-learning or meta-training our model can help to improve the accuracy of diagnosis.
Can you talk a little bit about the degree to which it improves over the existing methods? I think you guys are the state of the art now. What level of improvement did you achieve?
Do you mean in terms of numbers in our metrics? Or
Yeah, I mean, I guess we haven't talked about AUC and ROC yet, but I think that was the key diagnostic you guys used. I'd love to hear just a little bit more about how you evaluated your model and how it compared to the previous findings of other researchers.
Yes, our proposed approach improves the best baseline by 5 points. So from an area under the curve of 0.85, which is obtained using multiple instance learning or multitask learning, we improve it to a 0.9. And compared to DenseNet, we improve by 7 points. The importance of the ROC curve is to remove the effect of highly imbalanced datasets between classes that we use in medical imaging. And it is important when comparing systems because, for example, maybe a system, it's better when you have a true positive rate, right? It may have a fewer false positive rate than another system. But maybe system 2 has smaller false positive rate and a higher true positive rate than the first system. So the area under the curve is a global measure to compare these two systems. And what you try to do is maximize this area under the curve.
So your work achieved then a 0.9 AUC, which is quite high, actually, I think, by regardless of what the application is. I'm curious, do you know anything about how well a human radiologist would perform compared to that?
So there has been some papers claiming human level performance, but I think this is a bit controversial because even though you may show with a particular data set it's achieving human level performance, it's tricky because it's a human who has labeled those images. So I don't know, it's a very controversial topic in the field.
And I've had on a couple of guests and invited them to present some of those results about having achieved or exceeded human level accuracy, yet I haven't given that much treatment to the controversy. So I hope this does not sound like an ungrateful question because, as we stated, you've now achieved one of the state-of-the-art for the published literature, but you didn't get a perfect AUC. What's missing? What will get us from 0.9 to 1.0?
And I'm sure this is part of it, getting more examples, right? But it's also very difficult that one machine learning system will achieve an area under the curve of 1. There will always be some variability that won't be captured by these systems. But to improve this, I'm sure that we can design better ways to train these systems, incorporating, for example, non-imaging data, or by extracting some information, or by mixing this information with some other different modalities.
As you guys know from listening to Data Skeptic, we love to dig deep into topics that we're fascinated by. We're all about lifelong learning, and I'm pretty sure you wouldn't be listening to this podcast if you weren't as well. So I want to tell you about one of my other favorite ways to learn, and that's with the Great Courses Plus. The Great Courses Plus has this epic library of video and audio content, and your membership gets you an unlimited access to stream that entire catalog. I recently started The Inexplicable Universe with Neil deGrasse Tyson. I'm queuing up The Science of Information for myself next. I think that one's going on a flight with me. But the course I want you to think about checking out today is Mathematical Decision Making, Predictive Models and Optimization. This is a course from Professor Scott Stevens of James Madison University. Whether you're a newcomer to data science or a seasoned veteran looking to fill in some of the areas you skipped over a little bit, this 24-lecture series comes in 30-minute increments. Check out the first one and see if it's for you. If not, learn from engaging professors and experts about any topic that interests you, from math, engineering, astronomy, history. There's no shortage of content. And we've got a special offer for you this week. We know you're going to love the Great Courses Plus just as much as we do. For a full free month of unlimited access to all their lectures, go to this special URL. It's thegreatcoursesplus.com/data. Let me give it to you one more time. thegreatcoursesplus.com/data. I'm also curious to hear your thoughts about overfitting. In a case like this, it must be something that you think about because the data set is small and the feature set is large. How can you be sure you haven't just overfit the function?
Well, these are also a really good question. So when I start doing the experiments for the baseline, and I started with the DenseNet, it overfitted straight away, right? It didn't take many iterations to overfit and not be able to generalize. So our approach to try to reduce the overfitting was to reduce the number of parameters in the model. But with these data-driven approaches, I think overfitting is something that we are still fighting against. And it's the methodologies of training that will be need to improve to avoid this overfitting.
I'm curious, do you have, we live in an era now when there's a lot of discussion about model interpretability. Do you have any sense about what it was in your methodology that allowed this greater level of accuracy to be achieved?
Yes, so we are now working in the interpretability of this model. So we can, besides giving a malignancy probability, we can highlight some regions in the image about the malignancy of a particular image. What we are seeing is that compared to traditional approaches where the first to decide about malignancy, the first thing you do is localize the lesion and then classify it. The model interpretability cannot be as precise as these traditional systems at highlighting lesions.
One of the other areas that's kind of novel about the paper that we haven't touched on yet is the task sampling. I was wondering if you could describe for me how sampling is kind of uniquely done in your meta-algorithm and why that contributes to the overall solution.
Yes, so this is related to what just talked about how we learn. So the order you present tasks to the system may affect its performance in a new task. But this goes back to what we've been talking about a kid going to school. You want to present easier tasks first. So inspired by a paper by Matthiesen and collaborators last year, we choose to present the task to learn by its increasing the difficulty. But how do you define difficult? Because different things are difficult to different people, right? So what we do is we look at the model and we look at how well the model is performing on each task, and we choose to present easier tasks first. So when it masters an easier task, it can proceed to the next one.
And tell me a little bit about how you determine the ordering of those tasks and when you think it's ready to move on to the next one.
So this goes back to the approach presented by Matthiesen and collaborators, and it's called teacher-student curriculum learning. What it does is measures how much the model is improving in a particular task. So, for example, if you try a task and you improve your performance from 0.4 to 0.5, and you then choose another task and you improve from 0.4 only to 0.41, you will choose to give again the first task because you have learned more, which means that it seems that it's easier for the model to learn first that particular task. And a cool thing that they present in the paper is that when you have learned a new task and you proceed to the next one, you don't want to forget about what you have learned before. So for example, if you achieve performance of 0.9 in task 1, and then you're training on task 2, but the performance in task 1 goes back to 0.8, for example, you will sample or you will choose that first task again to master it first.
Well, one thing we haven't touched on yet is sort of the algorithm inside the algorithm here. Are we talking about deep learning neural networks that we're training?
Yes, so basically, if we train this low capacity just with 26,000 parameters denseness, as done traditionally, we achieve an area under the curve of 0.83, while if the same model is first meta-trained, we can achieve a higher performance. So the underlying model is the same in all cases. What is different with the denseness multiple instance learning or multitasking and our approach is the way that underlying model is trained.
So you obviously had good success on this one particular application. I'm curious if you've looked into other domains or if you see the potential for your techniques and methodology to be applied maybe even outside of the medical field.
So meta-learning is really popular in the robotic field, and there is a lot of research going on. But going back to medical image analysis, I think it has a great potential to analyze images from rare disease. So I think one of the main points of the paper is that we can train machine learning systems to perform well on tasks where we don't have enough training data. So for example, there was a recent paper trying to apply a standard computer vision technique to detect malignant cancer in mammograms, and they use a lot of data because there is a lot of data about mammograms. But there are other diseases where we may not have such a big amount of data or because it's difficult to collect. So I think this is one of the main applications of meta-learning in medical image analysis, try to focus in rare diseases.
Yeah, it's exciting to see a lot of the work going on in the area. I happened to catch your paper when it came out on the archive, but I think it's since been accepted to a conference. Can you tell me about where you're headed next?
Yes, so it's just been accepted to the conference MICAI, which is Medical Image Computing and Computer Assisted Intervention, which happens to be the most relevant conference in the field of medical image analysis. So yeah, I'm very excited. It's also in Granada. I'm from Spain, so I'm very excited to go back and be able to present my work there.
Very cool. And what's next for you? Is there a continuation along this line, or was this just one part of a bigger picture for you?
Yeah, so this research is part of an Australian research council. We're working here at the Australian Institute for Machine Learning at the University of Adelaide. I'll be finishing my PhD soon. The exact application is not really clear, but I hope to keep applying and designing these machine learning methodologies and to improve the performance of doctors in the clinical practice.
Well, I think it's a very excellent and ambitious path to be on, so I'm very curious to follow your career and see where that goes.
Yeah, thank you very much for the interview.
Well, maybe to finish up, I'll ask you one sort of philosophical question.
Yes.
I like the paper and the approach makes sense to me and all that, but to be a devil's advocate, maybe I could say, well, this is perhaps, you got some nice improvement, that's all well and good, but why do we want machine learning to necessarily do it the way radiologists do it? Sure, maybe it works for them, but maybe a purely computational approach should be more exotic in the way it happens, and we shouldn't limit ourselves by behaving like mere mortal humans.
Well, we've seen that in the last couple of years, we've seen a huge improvement with the performance of models just by giving lots of data, right? So, But it seems that this is saturating now, so we need to find new ways for training this model that can improve the traditional way of training these models. Initially, it seemed to us that following or trying to imitate how humans learn, it might improve results. That was our initial hypothesis. And it seems that just building models that with increased capacity, it seems that it's saturating and, there is no clear next step there. So by designing new methodologies that improve the way the model learns, it's showing good performance. And we humans, we can learn efficiently, we can learn quickly and from few images. So why not? Machine learning can imitate that.
Yeah, absolutely. Well, Gabriel, thanks again for taking the time to come on and share your work. It's a very interesting paper.
Yeah, thank you very much for having me again, and it's my pleasure.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.